everybody. My name is Paulo Rodrigues. I'm a consultant anesthesiologist in Lisbon, Portugal. And thank you very much for attending our basic and clinical science anesthetic course. I'm an old-time ERIC examiner and also a member of the committee that organizes this course. This lecture is a summary or tries to summarize opioids and some of the most relevant information regarding opioids. And I have no conflicts to declare regarding this subject. And our outline will be the one that is showed now. We're going to definition and the classification of opioids, and then we'll speak about the receptors, some details about the biased agonism and the mechanisms of action, and then we'll go to brief summaries of pharmacokinetics and pharmacodynamics and some details about the new opioids. So, opioids are drugs derived from opium, the latex juice, the latex juice of the poppy that you see here, and that is collected and prepared. And this juice, after being dried, we may extract from these juice many alkaloids, sugars, water, and even meconic acid. And these alkaloids belong to several groups, including the morphine alkaloids, morphine, codeine, theanine, and oripivine, and also many other drugs that may be or used or not. And so these opioids may be classified in several ways. So they may be classified as exogenous or endogenous opioids. And regarding the exogenous, in the way they are synthesized, about their chemical structure, the potency, the type of affinity for the receptors, and its effect at the opioid receptor. So there are several different ways of classifying opioids. And for instance, regarding exogenous opioids and the way they are synthesized, they may be classified as naturally occurring, and the one, as I said before, more used is morphine. And then there are the semi-synthetic, like the theanine derivatives, atropine and buprenorphine, and the ones that are fully synthetic. And these are the ones that we most use today, mainly the phenylpiperidine derivatives, such as meperidine, fentanyl, sufentanil, alfentanil, and remifentanil. And according to their chemical class, they can be classified as the phenanthrones, the benzomorphins, the piperidines, and the diphenylheptanes. And of course, this is important just for you to understand that the ones that we use mostly today are from the group of the piperidines, such as alfentanil, fentanyl, remifentanil, and sufentanil, and also the ones that come from the chemical class of the phenanthrones. And by its potency and based on the plasma concentrations at which the opioids exert their effects, and taking morphine as the base for considering the relative potency of all the others, it is important to know that our most used opioids, such as fentanyl, are much more potent than morphine. So fentanyl is about 100 times more potent than morphine, sufentanil 1,000 times, alfentanil about 20 times more potent than morphine, and remifentanil about 100 times more potent than morphine. So they may be classified as the strong opioids, the ones I've mentioned now, the ones with intermediate potency like morphine, methadone, and buprenorphine, and the ones that are weak like codeine, hydrocodone, dextropropoxifen, and tramadol. Regarding the affinity for the receptors, they may be classified as agonists, so pure agonists, such as morphine, meperidine, fentanyl, etc. The ones that have antagonists and antagonists or partial agonist effect, like the one as buprenorphine that we use regularly. The ones that are total antagonists, like nalorphine, naloxone, naltrexone, and the ones that are nowadays classified as the biased agonists, such as oliceridine. So what is this of the biased agonists? It's drugs that or compounds that stabilize a conformation of the target receptor, in this case the mu opioid receptor, causing it to preferentially couple with a specific intracellular pathway while not coupling to others. We'll come to this later on in this lecture. So a biased opioid has the potential to act as an agonist for a certain pathway and eventually simultaneously being inert or even displaying inverse efficacy for the other pathway of the receptor effect. Finally, we have endogenous opioids, and these are agents found throughout the body that act on an opioid receptor, and we know three main classes, the enkephalins, endorphins, and dynorphins, that have different affinities for the opioid receptors. They are involved in a variety of regulatory functions, such as nociception, stress, emotions, hedonic responses, and on the modulation of thermoregulation, breathing, neuroendocrine function, gastrointestinal motility, and immune responses. Opioid receptors act on these, opioids act on receptors, which are peptides. And we do know that are three main opioid receptors from the mu opioid receptor class, mu1, 2, and 3, and also the K opioid receptor, core COP, or the delta opioid receptor, and the orphanine nociception receptor, and this is the one and only that is not sensitive to naloxone. These receptors are distributed throughout the brain and the spinal cord, and also outside the central nervous system, such as vascular tissues, cardia, airway, lung, gut, and on cells of the immune system. So what happens when an opioid, an agonist, binds to the receptors? So let's see in this image the left side of the image, this one. So after binding to the agonist, it causes a dissociation of the G protein into alpha and beta delta subunits, and this inactivation, this dissociation causes the inactivation of calcium channels and the activation of potassium channels, inhibition of adenyl cyclase, and the stimulation of mitogen protein kinases. So an opioid that has a bias towards this G protein signaling has been linked to the anti-nociceptive or analgesia profile. On the contrary, if you look at the right side of the picture, so the other pathway, it's the B-arrestin signaling pathway. So here what happens is this activation of G protein receptor kinases leads to the internalization and desensitization of opioid receptors and the activation of mitogen-associated protein kinase in cascade, which comes to a bias of, towards the beta-arrestin and the activation of this pathway has been linked to the side effect profile of opioids. So actually, if you have a pure and unbiased agonist that interacts equally both pathways, the left pathway and the right pathway, so you will have a drug that has both effects, analgesia and also the side effects. But if you have an opioid that has more predominant actions on the left pathway, you will have more analgesia and less side effects. On the contrary, if you have a bias to the right side of the pathway of the receptor, you will have more side effects and less of the desired effects, which are mainly the analgesia profile. So this is what we call nowadays the biased agonism at the mu-opioid receptor, which is being subject of extensive investigation. So how does analgesia comes? Opioids may produce analgesia through peripheral mechanisms, so immune cells infiltrating the inflammatory sites may release endogenous opioid-like substances that may act on opioid receptors locally, located primarily on the sensory neuron, and then I'm sorry for the delay. They may also directly inhibit ascending transmission of nociceptive information from the spinal cord dorsal horn, and also activating pain control circuits that descend from the midbrain via the rostroventral medial medulla to the spinal cord dorsal horn. So these are the proposed mechanisms of analgesia for opioids. So regarding pharmacokinetics and a summary of pharmacokinetics, you must remember that opioids are weak bases, which are dissociated to an ionized and base fraction, which are dependent on the pH of the tissues and the pKa of each drug. So the ionized fraction is less lipid soluble and will be attached to plasma proteins and not available to diffuse to the action site, which contains the receptors. So despite not being able to diffuse, it is the effective form of the molecule that the receptor will recognize and produce its effects. On the contrary, the base-free fraction is more lipid soluble and free to diffuse to the action site. After IV injection of an opioid, you have an initial rapid peak in plasma concentration, and the changes over time can be described by non-compartmental and compartmental pharmacokinetic models. So lipophilic opioids with low protein binding affinity, such as fentanyl and sufentanil, which have a very high volume distribution of approximately 300 liters, will have a main effect caused by redistribution, accounting for the loss of analgesic effects in drugs such as these ones. And for instance, on remifentanil and alfentanil, which have lower volume of distribution and have different mechanisms of elimination. For instance, remifentanil is mainly due to high clearance, and alfentanil is mainly due to high protein binding, and the clearance will be responsible for the drop in plasma concentration. Regarding the metabolism, most of the opioids are metabolized in liver, And morphine, for instance, is metabolized into several different metabolites which still have significant activity, and mainly due by the cytochrome P3A4 and P2D6 involved in biotransformation of morphine congeners like heroin, codeine, and fentanyl. There's a high genetic variability, and so we may have to be cautious because there may be increased or decreased activity of the cytochrome. On the contrary, remifentanil is metabolized within erythrocyte and tissue non-specific esterase, and so it is not dependent on this liver function. Regarding excretion, most of them are excreted by the kidneys and or by the biliary tract into the gut. And in kidney, morphine and its derivatives are excreted by glomerular filtration, which may cause in patients that have renal failure for elevated levels of these metabolites and may lead to adverse effects such as seizures or central nervous system depression. So we are not going to this. It has been detailed in previous lecture, but this is a very frequent question we do have in NIDAC Part 2. And the question is as simple as this. Please draw and explain context-sensitive half-lives for fentanyl, and several other opioids, such as remifentanil, and explain. And indeed, very contrary to remifentanil, the ones such as fentanyl accumulates with time, and due to its pharmacokinetic properties, and you will have to explain why. Regarding the effects on the body, the pharmacodynamics, analgesic effects are effects which are very variable in people. And regarding the brain, it's typical to have CNS depression, changes in cerebral blood flow and metabolic rate, respiratory depression, depression of cough, and eventually seizures and convulsions. And as you know, we can use opioids only as the sole anesthetics in cardiac surgery, for instance. Regarding the peripheral effects, it's quite typical to see nausea and vomiting, smooth muscle effects, relaxation, skeletal muscle effects, histamine release, pruritus, pupil effects, and other diffuse central nervous system effects, cardiovascular and immune system changes. And these immune system changes are very relevant in today. We'll come to this later on. So it's been developed, the peripheral acting new opioid receptor antagonists, trying to counteract these peripheral effects, and these some of these have been proved recently and are being used in clinical practice, but not very extensively. Opioids and the immune system. So new opioid receptor, as you know, it's highly expressed in some forms of tumors. And it's been proposed that opioids may be capable of stimulating angiogenesis and lymphangiogenosis. And so it's been suggested that propofol-based anesthesia plus regional anesthesia may eventually have better results regarding opposite to vapor and opioid anesthesia regarding the expression of tumoral cells. So new opioids such as the biased opioid oliceridine has been introduced into clinical practice in August 2020. It exhibits approximately a threefold preference for the G pathway. So the left pathway I've mentioned, really over the the right pathway, the B-arrestin pathway. So with fewer side effects, has a potency equal to morphine, hepatic metabolism, but no active metabolites. And there is no dosage adjustments in patients with renal impairment. So it's a quite new drug being used mainly in the United States for the moment. Also, tapentadol, there are some trademarks referred. It's also, such as tramadol, norepinephrine reuptake inhibitor. It has moderate mu-opioid receptor agonist effects at spinal and supraspinal sites, and mainly it has less side effects compared to tramadol, with minimal serotonergic effects and lower tendency or liability for abuse. So this is our references. You may email me also regarding some references that I may provide to you. Thank you very much for attending this lecture, and see you soon. Thank you. So one question that may be asked to you is, could you please describe the pharmacologic rationale behind the development of biased opioids?